So today, Richard is going to talk about his work with John and Nicholas on the ZXH.
It's also missing Adolfo Grushin on there. That's
Oh,
not an oversight of mine. No, it's my oversight.
Oh, yeah.
I don't know how his name went missing. But yes, the paper itself also involves Adolfo Grushin as a key part of it, in fact. And that is the paper listed there. Okay.
Yeah.
So what am I talking about? The general idea is in condensed matter, you have a lot of discussion about tensor networks. A lot of things are phrased in terms of tensor networks. And even when they're not maybe the underlying mathematics that's being worked with, they're still used as a default way of approaching a problem. They're pretty good at that, and they have lots of excellent applications. And they even have some in-diagram rewrites. That is to say, you can say a couple of tensor networks are equivalent to each other. But in the end, they're ultimately just a pictorial assistant. There isn't a complete language for rewrites or even a sort of practical fragment. You probably all know about the ZX-calculus. It has a complete language. It is basically a tensor network. The diagram is the mathematics. You don't have to defer to what it's interpreting. You can just work with the diagrams themselves. However, in general, you're working with C2 maps. That is to say, you're working with qubits or collections of qubits ultimately. And if we're talking systems, often you'll want to talk about things of multiple spins, or different spins, spin 1, spin 3/2, so on and so forth. And that's not obviously related to qubits. And we've solved these problems. So the idea, let's take a condensed matter system, and we're going to view the diagram as the calculation itself. No falling back to some underlying interpretation. With that in mind, we focus on AKLT states. So these were invented really by Affleck, Lieb, Kennedy, and Tasaki when they wanted a one-dimensional state with a valence bond between every pair of sites. You can also view that as a singlet between every pair of sites. And the way you view it is those singlets pair up, and together they get projected to a spin 1. So sites here you could view as points in a lattice. For the AKLT state, it's just a single line of spins. But the point is these singlet states are being paired up to make spin 1 sites. So two of them come together to make a spin 1 somehow. And here we have a sort of depiction of that you'll often see if you look up literature. Now, why did they make an AKLT state? Well, unsurprisingly, because there is an AKLT Hamiltonian that they wanted a ground state of. Now, it's not obvious here, but the AKLT Hamiltonian asks a question, basically. It says, if I take 2 sites, that's 2 spin 1 spins in your lattice, or in this case, just a straight line, is it spin 2? If it is, then you have a non-zero number. If it isn't, you have 0. That's basically what this Hamiltonian asks, if you view it as a spin 2 projector, which you can. So what the AKLT state does is it is a system that cannot be spin 2. And it does this by virtue of those singlets, because if you think a singlet is a spin up and a spin down on each end. So if you have a collection of these, there is no way to form a spin 2. You can't have 4 spin ups in a row. And so they made this state to demonstrate that point. Now, a little bit later, it was noticed that this, as well as being something that satisfies the AKLT Hamiltonian, this state has a non-trivial topological property. Specifically, it is a diluted ferromagnet. To understand that, if you think of normal ferromagnetism, which you may or may not be aware of, you have a line of spin up, spin down, spin up, spin down, spin up, spin down, going on continually, canceling each other out. A diluted ferromagnet is basically the same thing, except you can have zeros padded in the middle. So if you think of a spin 1, you can have +1, you can have -1, that's sort of your up down. You also have zeros, and they act as sort of padding. So a diluted antiferromagnet rather, is going to give you this up-down structure with zeros in between. Now, the interesting point here is the AKLT ground state must have this property, but it is a property that is determined at a distance, if you like. You could have a spin +1, you could have an enormous number of zeros, and then you have to have a spin -1, or another zero, of course. You cannot have another spin +1. So in this way, you get a sort of topological global property that isn't localized. And often people talk about string order parameters. Well, they talk about order parameters. In this case, you have a string order parameter, which looks hideous. All it does is test, okay, is this true or not? Do we have this property or not in this state? And it gives you 0 if it doesn't, and non-zero if it does, I believe. Okay, so let's talk about tensor network states. Slightly, it'll all come together in the end. Tensor network states are alluding back to the idea of tensor networks being useful in condensed matter physics. They are essentially a depiction of a state or representation of a state in terms of some tensor. Within this set of states, you have matrix product states, which are a one-dimensional array of tensors. Now, notice how we've moved from talking about physical systems in and of themselves to discussing representations of physical systems, how they are described. An important point, and the reason I bring up MPS in particular, is because it is the core element in the headline algorithms of condensed matter physics, or numerical condensed matter physics anyway. That's things like DMRG, density matrix renormalization group, and the time evolving block decimation algorithm. Unsurprisingly, since it has a tensor network representation, you also have tensor network diagrams that are associated with this. And in the literature, you will see things like this, an MPS representation of a tensor network state, or specifically a matrix product state, as a kind of diagram, which directly relates back to Penrose. So you can see the sort of genealogy that overlaps with the sort of things you'd be thinking about with the ZX-calculus. Okay, so we've talked about MPS and tensor network states more broadly. And I mentioned the AKLT state earlier. There is a reason I did that. It's because they overlap. And you can represent the AKLT state as a sort of tensor network diagram, or specifically matrix product state diagram. Here you can see these sort of orangey, I'm going to say, maroony perhaps, somewhere in between those two colors, bars, and they represent singlets. And then you have these sort of gray circles with dots. These represent projectors on those singlets, but in some sense that we'll get to in a bit, give you the spin 1. To say that again, it takes in these sort of pairs of either end of pairs of singlets and gives you a spin 1 out of them, or gives you the space of spin 1. So ZX-calculus. I won't labor these points because you know what it is. You have some generators, some things represent states, some things represent operators. You have a Hadamard in there. It has some rules we all know and love, and they give you a sound and complete representation of cubic quantum mechanics. Here's a C0. There's a reason I bring it up, but in general, it's super useful and it's quite pretty in the ZX-calculus. And here's an example of how a C0 gets used when you apply state strut. So here's a motivating idea. We have a C0. We can imagine, well, we can, in fact, write generalized controlled rotations. Can we imagine multi-controlled rotations? And if we can, you could imagine for each basis that you could put into one side of a diagram, you could imagine that being sort of like selecting out an element of a matrix, the specific element, and then applying a certain rotation to it. And in that way, you could construct anything you wanted really matrix-wise, because you could be so specific about how each particular basis would be mapped. There's a problem though. In general, in ZX, you don't have very nice CC NOT gates, never mind generalizations to multiply controlled rotations. So now we talk about ZXH. We get there by a single extra generator, or if anything, adaptation or generalization of a single generator. And that is our lovely one-in, one-out Hadamard box has become multiple-legged. And as you'd expect from adding another generator, this adds a bunch of rules, some of which you'll be familiar with before through the ZH-calculus, and I will talk very shortly about that overlap, which is extreme. And here you can also see some practical additions. For example, we have the plain red explosion and the red pi absorption, which are rather critical when you're trying to design, at least in my experience, when you're trying to sort of design specific operators and construct them by hand. There are certain, not necessary rules, but useful axioms which are crucial in being able to actually do that. And there's an example of a couple there. Okay, so some of you know a great deal about ZH. Some of you are critical in inventing it. And you may have some slight problems with me coming out and saying, well, ZXH, look at it, it's lovely. Brand new calculus, how exciting. You know, you may be currently muted, shouting you're a fraud and a liar. And that's not entirely unreasonable, because you could view ZXH as essentially ZH with a new name, less minimal, and I've just kept the old colors. Obviously, this is in a sense true. You can see everything you're seeing here as syntactic sugar on top of ZH. But there is a reason to make this distinction. So practically, when working with this stuff, the focus on bases, you know, having the red and green, it's no longer sort of background consideration. It is at the front of your mind most of the time. On top of that, you have that physics, even in its ZHE form, is essentially ZX with multi-legged Hadamard's. And on top of that, the ZX literature itself, its design and with red, green, various Wikipedia pages, the various entry-level papers written on it, it's very accessible. The ZH has AND gates like we'd want, but the literature is, I would say, not as accessible, and it's heading in its own direction. You know, you have SAT problems addressed in it and other things that aren't directly related. And since this was a sort of interdisciplinary push, it felt sensible to sort of stamp down a variant, specifically ZXH, as a reference point for investigations into condensed matter systems. And I hope, even if you disagree strongly, this goes some way to explaining why we made the decision to explain the ZX, to demark the ZXH-calculus as a thing in its own right. Okay, so with that explanation out of the way, here is a lovely ZXH-C0 or ZH-C0. And with it, we are going to work wonders. Specifically, we're going to represent the AKLT state in a condensed fashion. So there's a lot going on here, but I'll talk through each point. With A, we're seeing the singlet, that bar that we talked about before. And immediately we have a ZX representation of that, and never mind ZXH. We also have a projector whose structure we will discuss shortly, but it gives that the part of the tensor network diagram we were discussing previously. In D and E, what we have here is, in D specifically at first, we have what I might call the literature representation of matrix product states. If you go into the literature, you will find, in condensed matter literature, you will find things that look like this. They are connections of tensors with some sort of outgoing wire that is called the site. It denotes the sort of points on the lattice or points on the line I mentioned earlier. Now, these are specific matrices that usually get used in the literature. They're not specifically fixed, but there are standard ones that people tend to use. As such, we've identified how those specific ones can be mapped to ZXH diagrams. So you get a sort of translation between what exists already and what we've done here. And in F, you see a collection of these MPS matrices, which form the AKLT state. And you can see how this is going to work. You know, you've got the lovely magneto square there that illustrates where your spin 1 site is. You can see how each spin 1 is connected by a bunch of singlets. And there's some sort of projector-like object on top, which, as I'll demonstrate, is going to give you the spin 1. Okay, so here are the key elements here for this AKLT, 1D AKLT state. You have the projector and you have the singlets. Notice when we put them together, we're going to identify immediately a key property that gets brought up about AKLT states, namely that they have spin half edge states, sort of dangling degrees of freedom at the right and left side. Now, these are obvious from a ZXH perspective. You would, of course, draw them in a tensor network diagram, but because you don't have the mathematical guarantees that come with a ZXH diagram, you wouldn't immediately necessarily know, yes, you have those degrees of freedom there to work with. But here, there's no question. Furthermore, we talked about the order parameter earlier, the way of identifying the diluted ferromagnetism. Now here what we're doing is we're going to demonstrate this entirely diagrammatically. So here you've got an AKLT chain, an AKLT state, where we've applied the spin 0. That is the spin 0 in the terms of a spin 1 representation, if you follow me, as in you have +1, -1, and the 0 in the middle. And we're going to apply the 0 to these intervening sites. And at the end, we have the left and right ones free. By doing that, we can see, or we should be able to see, that antiferromagnetism gives a non-zero order parameter, which implies that it is possible. And ferromagnetism does not. It gives you 0, so it's not allowed. Okay, so to show this entirely diagrammatically, first we just say, okay, what happens when we apply the different options that we can apply to spin 1? Remembering that two red spiders tensor producted together is going to be 0, 0, which is mapped to +1 for spin 1. We have the cap with a red pi on it, which you can check yourself is equivalent to 0, 1 plus 1, 0, which is your spin 0. And then on top of that, you have a tensor product of pi, pi, both being red, and that will give you your spin -1. So we can apply that to the sites. We can apply the diagram rules that we have, the rewrite rules that we have, and we can see they collapse very nicely, in fact. So nicely, we can boil the entire problem down into a much smaller one. So we've taken a very large chain, very complicated object, and shrunk it down. The zeros, it turns out, add very little. The padding adds very little outside of a small green pi that appears depending on whether it's an odd or even number in between the two sites you're interested in. And from that, we can immediately show that if you apply 0, 0, or sorry, +1, +1, or -1, -1, these won't be allowed. These will give you your zeros, while a -1, +1 will give you what you require, and this will be allowed. So we can detect a topological phase entirely diagrammatically. Okay, but the 1D AKLT, not that exciting. It's from the 80s, spin 1. It's a chain, very nice, very interesting, great stuff. Weird though, we've been talking about spin 1, and as I've been alluding to throughout, we only really work with spin half, or at least spin half is our sort of bread and butter in ZXH. How do we get higher spins? So this is now where we're going to go back and talk about those operators, that projection operator. So within representation theory, if you take SU2 and you take the fundamental representation, you can build the higher irreducible representations, that is to say spin 1, spin 3/2, spin n/2, by taking n copies of the fundamental representation and taking a symmetric subspace. To say that again, in language that makes more sense probably, if I take n qubits, that's n spin halves, and I take the symmetric subspace of that, I have spin n/2, or I have the space of spin n/2. So let's look at this again. What does it do? Well, this part in the middle, it is a doubly controlled gate that you may or may not be able to see, depending on your expertise in these things. When triggered, will project something to 0. And the things either side basically change the basis and change it back again. If you look at exactly what it does to sort of qubit elements, you will see that if you look in the triplet singlet basis, that is to say the symmetric basis plus the singlet, you see that it throws out the singlet. It throws out the anti-symmetric component and leaves us only with 0, 0, 0, 1 plus 1, 0, and 1, 1, which, if you know a bit about these things, is the spin 1 space. But I said symmetrizer, and this doesn't look very symmetric-y. So how is this thing giving us a symmetric subspace? Well, here I give you a little diagrammatic proof of how the thing on the top left is equivalent to the thing on the bottom right. The thing on the bottom right is a controlled swap gate, but it's coherently controlled. So what it's doing is it is the action of doing nothing, just the identity, plus the action of swapping those wires over. Now, if you think about it, if you add something to its symmetric counterpart, the anti-symmetric components will vanish because they will become a minus when you swap things over, and they will cancel when they add them. You can think of this in matrix terms. So only the symmetric part will remain. And this is how we take two spin halves, build its symmetric subspace into a spin 1. Okay, but higher spins. So this argument is courtesy of John, to give credit where credit is due. And this is a way we can take basically permutations of n wires and turn them into a permutation of n plus 1 wires. The idea is basically, when you do this spin spin 1 trick, we were taking two permutations, 1, 2, 2, 1, and we added them together. If I now want to permute 3 wires, well, a sensible way of doing that is to say, well, I have 1, 2, and 2, 1 already from this operator I did previously. Now, if I apply a couple more swaps, I can say, I want to put the 3, this new wire, this new permutation wire coming in. I want to put it in the top position. I want to put it in the second position. I want to put it in the third position. And since I'm already swapping 1 and 2 over, this is going to give me every permutation. It's going to give me 1, 2, 3. It's going to give me 1, 3, 2. It's going to give me 3, 2, 1. To understand this more concretely, let's look at the spin 3 over 2 example. So on the left, we have something that swaps over 1 and 2. It's a permutation of 1 and 2, or not, if it's the identity, because it's coherently controlled. And secondly, we have this, this operator that is going to, if you like, insert 3 into every possible position. Where, remembering that this object at the top acts as a control for this gate, you see we get 0, 0, 1, 0, and 0, 1. That is, in a sense, do nothing, do the first one, do the second one. So if I take a permutation, let's say in the first state, we do nothing. One of the coherent elements, one of the superpositions of these gates, this action, is going to do nothing. So we've got 1, 2, and 3 hasn't been touched, so it's 1, 2, 3. And then let's say we apply, we're in the superposition element where the second one is applied. That is to say 1, 0. So now 1 and 2, 3 is going to become 3, 2, 1, because the first and the last have been swapped over. And since I'm going to do this every possible permutation, this is going to give me that symmetric subspace that I'm looking for, but now over 3 wires. And since we have a general way to extend this, we can get the general spin. We can get any irreducible representation of SU2 from the fundamental representation, which is what we have to begin with because we work with ZXH. Now, with 3 over 2 in particular, we can take a 2D AKLT state. It's the same game. We have some projector, this time on 3 spin halves, which emerge from 3 different singlet states. And they connect in a big lattice. The one we're interested in is hexagonal, where on the left you see the sort of image you might see in the literature of condensed matter physics. And we can show that this is equivalent to a quantum resource, specifically a cluster state. Now, firstly, we're going to do this via showing entirely diagrammatically that what we've described, this 2D lattice, after having certain projections applied to it, will give us a graph state. And we can do that diagrammatically. Firstly, let's remind ourselves what a graph state looks like in ZX or ZXH. It's going to look like this creature at the bottom. A graph state, naturally, is related to a graph. The way you see that, or the way you convert one into the other, is you take each vertex and you imagine that is a site or an emerging wire. And between each edge, between those graph nodes, you have a Hadamard wire. Okay, this is a slide explaining exactly what I just described. Okay, so I mentioned some projectors that need to be applied. These are those projectors. Together, they make a POVM measurement. So what you can imagine is if we have this big lattice and we're going to apply this particular measurement at each site, I'm going to get one of these actually happening. So it's a slightly random situation. We can show entirely diagrammatically again that with the action of these previous projectors, the sites will reduce. The projectors that we see reduce considerably. In fact, technically they're eigenoperators, which is quite nice. So that large diagram we had before with the symmetrizers representing the hexagonal lattice is now reduced to this thing. Now, if you know a bit about Clifford ZX, you know that we're only seeing Clifford gates here. So this must be equal to a graph state. But can we show it explicitly? So we use a bit of trickery now. We try as much as we can, and succeed, in fact, on moving all the intermediary parts of the, or interstitiary, perhaps, parts of the sites that we see in this diagram onto external wires. That is to say, sort of onto the site wires, if you will. Now, when we do that, essentially, since these wires are external, we're free to gauge transform or change the basis, if you will, to remove them. So we have this sort of squiggly wire argument. And if you look at the paper, you'll see that there. We will move things, these rotations onto external wires, and then basis transform them away, if you will. And by doing that, we turn the slightly convoluted hexagonal thing we had before into something very clean. Here in the left of the large lattice, we see the hexagonal lattice where we've just labeled randomly some projector that happened. You remember it was EX, EY, EZ. And here I've just labeled, okay, let's say it's YY was here, XX was here, Z was here, so on and so forth. And you can see that if they're different, it turns out that you get a Hadamard wire between them. That is a wire with a Hadamard on it. If they were the same, you don't have anything, which means you can contract them via standard ZXC rules. Following through on this, you contract, you remove the sort of doubly connected things, and you arrive at something that looks almost like a graph state, except it has too many edges on things. However, if you remember, this is a sort of rank 1 tensor. That is to say, there's not any extra information in these extra wires. They too can be sort of basis transformed away in a sense, because they didn't contain any extra information. If it helps, you could imagine putting on a green spider, which had all the legs that are coming out of this particular site, absorbing them and then fusing them together and just having one leg out. Now, this would do nothing to the information. And in this way, via basis redefinitions, we arrive at a graph state. And this has all been done via diagrammatic considerations, essentially. Now, not any graph state is a universal resource. A cluster state is a universal resource state. Now, this is not a result we deal with, and it is not a result we did diagrammatically, because it's more out of statistical physics and a percolation argument, if you know much about that. Now, basically, it tells us if you have a sufficiently sized lattice of this form, with high probability, you will be able to get a cluster state. It boils down to a connectivity argument of this graph that you end up getting. So what did we do again? There was a lot here. We took a 1D AKLT state. We wrote it in ZXH. We identified spin half degrees of freedom on its ends, and we showed it possessed topological order entirely diagrammatically. We took the 2D AKLT state. We invented a way to represent SU2 representations, read spins there if you like, in ZXH. And then we wrote the 2D AKLT state in ZXH. Then we proved diagrammatically again that if we're applying certain projectors at each site, you would get a graph state. And then we reasoned by a well-known result, or at least a known result, that this with high probability will give us a cluster state. Now, this wasn't quite our result, but it is how we rounded off the paper. And that concludes what I have to say today. Thank you for listening.